Today I'll discuss about question answer on fluid mechanics. From that you can test your knowledge on fluid mechanics. So question number 1 is, what is an ideal fluid and how does it differ from a perfect and real fluid? So ideal fluid, a theoretical fluid with no viscosity and incompressible, used primarily in theoretical analysis. What is perfect fluid? It is similar to an ideal fluid but may include additional assumptions such as absence of heat conduction, used in relativistic physics to model matter properties. Real fluid exists in the real world with properties like viscosity, compressibility and thermal conductivity. Example, water, air and oil. Next question, what is a Newtonian fluid? Provide examples. Newtonian fluid follows Newton's law of viscosity, where shear stress is directly proportional to the velocity gradient du by dy. So tau is equal to mu du by dy, where mu is the dynamic viscosity. Example, water, air and most common fluid. So next question is, what are the non-Newtonian fluid and how do they behave under shear stress? So non-Newtonian fluid doesn't follow Newton's law of viscosity. The relationship between shear stress and shear rate is nonlinear. Types includes shear thinning, that is ketchup, shear thickening, that is cornstarch and water, and viscoelastic, that is polymer solution. Example, ketchup flows more easily when second, means shear thinning, while cornstarch and water mixture become thicker under pressure, that is shear thickening. Next question, classify non-Newtonian fluid and give examples of each type. So non-Newtonian fluid classification, so pseudoplastic, shear thinning, viscosity decrease with increasing shear rate, example paint and slurries. Dilatant, shear thickening, viscosity increases with increasing shear rate, example silly putty and quicksand. Bingham plastic, exhibit a yield trace below which no flow occurs, example to toothpaste and mayonnaise. Plastic that rigid until a critical trace is exceeded, example modeling clay. Thixotropic, viscosity decreases over time under constant shear, examples certain inks and gel. Rheopectic, viscosity increases over time under constant shear, examples some drilling muds. Now question 5 is, what is the vapor pressure and how does it relate to evaporation and boiling? So vapor pressure, what is that? Pressure exerted by a vapor in equilibrium with its liquid phase at a given temperature, and vapor pressure indicates the tendency of a substance to evaporate and increase with temperature. Evaporation process where molecules in a liquid gain energy to enter the vapor phase occurs at the surface of the liquid, and endothermic process absorb energy. And boiling, liquid turns into a vapor throughout the mass, occurs at boiling point when vapor pressure equal to the atmospheric pressure. Now question 6, define surface tension and its significance in fluid. Surface tension, force acting at the surface of the liquid, minimizing surface area. Surface tension caused by cohesive force between molecules lead to phenomena like capillarity and droplet formation and liquid surface shapes. Surface tension unit Newton per meter, CGS dyne per centimeter. Water striders can walk on a water due to high surface tension. What is the compressibility in fluids and why is it important? So compressibility measure of how much a fluid volume decrease under pressure. It is the reciprocal of bulk modulus, important for understanding how fluid behaves under varying pressure conditions such as deep sea or high altitude environment, mathematically expressed as beta is equal to minus 1 by v dv by dp constant temperature, where beta is the compressibility, v is the volume, p is the pressure and t is the temperature. Define bulk modulus and explain its significance in the fluid mechanics. Bulk modulus measure of a fluid resistance to uniform compression. It is the reciprocal of compressibility, indicates how much pressure is needed to achieve a certain volume reduction in fluid, mathematically expressed as K is equal to minus B dou P by dou V constant T, where K is the bulk modulus and V is the volume, P is the pressure and T is the temperature. Question number 9. Explain the relationship between surface tension and pressure drop in a droplet and bubbles. Surface tension and pressure drop. For liquid droplet, pressure inside is greater than outside, that is given by del P is equal to 2 sigma by R. For a soap bubble, pressure difference is del P is 4 sigma by R. Smaller droplet or bubbles have higher internal pressure due to surface tension. Examples: smaller soap bubbles have a noticeably higher internal pressure than larger ones, making them more likely to collapse quickly. Question number 10. What is the capillary rise and fall? Provide the condition that affect each. So capillary rise, upward movement of a liquid in a capillary tube driven by adhesive force between liquid and tube surface. Height of rise and fall given by Jurin's law, that is H is equal to 2 sigma cos theta rho g R. Capillary fall means downward movement of the liquid below the surface in a capillary tube, occurs when contact angle theta greater than 90 degree. Water rise in a glass tube but mercury falls due to differing contact angle. Now question number 11. Define surface tension and its significance in fluid. So force acting on the surface of the liquid, minimizing surface area, caused by cohesive force between molecules, leads to phenomena like capillary droplet formation and liquid surface shape. Water has high surface tension, that is 0.072 Newton per meter, allowing small insects to walk on its surface. Then what is the capillary and how does it affect fluid behavior in narrow space? So capillary means ability of liquid to flow in a narrow space without external force, driven by balance between cohesive force within the liquid and adhesive force between liquid and solid surface, observed in capillary tubes, porous material and small diameter tubes. Example: capillary rise of a water in a thin tube, capillary fall observed in mercury in a glass tube. That's it. Thank you.